Okay, it's 2:20, and our talk slots for this conference are very short, so I'm going to get started. All right, this talk is titled Determining Ruby Process Counts. This talk is really geared at anyone who has control over their dyno slider at Heroku, and you ever wondered what to set that dyno slider to. Or maybe if you use AWS, you want to know how many EC2 instances you should be using. We're just going to be talking really about horizontal scaling and provisioning of Ruby applications. Specifically today, I'm going to use a web application as an example, but this model is very generalizable to many different types of applications. I'm going to talk about how to apply this method to other application types at the end, but basically any Ruby or other language application which takes requests and has to serve responses can use this process I'm about to describe. My name is Nate Berkopec. I am a consultant. I focus on Rails and Ruby performance. I have a book called The Complete Guide to Rails Performance. You might have seen my blog. It's speedshop.co. It looks like that. And I teach workshops for Rails performance as well. I live in New Mexico in the United States. I volunteer for search and rescue there and spend a lot of time outdoors, spent the whole last winter skiing. In the future, I'm going to be living outside of the United States pretty soon, moving out in the next couple of months. If you live outside of the US and you think I should live in your country for a while, I'd really appreciate talking to you and I appreciate the recommendation. England, that sounds great. I'd love to. Okay, so this question is fundamentally an answer to the, this talk is an answer to the question of how many servers do you need? And in my experience as a Rails consultant, I generally get to see that most people sort of guess at the answer to this one. And at some point in the past, some guy or girl decided to just increase the number of dynos or EC2 instances until the problem went away and things seemed okay. And oftentimes I come into shops that are pretty heavily overscaled. So they're using way, way too many dynos or servers for their load. And that costs a lot of money. So this talk is really fundamentally about how we can help you spend less money or show you where you should spend more money. When I talk about Rails performance or performance in general, I say there are two things that we can do when we work on performance. One, we can improve the experience for the customer. So we can make the site feel faster, make the application feel faster and more performant. Or we can reduce the cost to deploy the application. Okay, so when we're working on performance, we're doing one of these two things. And this talk today is focused a little bit more on the second part. We're going to talk mostly about cost control, how to use less hardware to deploy your application. And this question can really result in thousands of dollars per month in savings, really almost regardless of the application size we're talking about. One sort of benchmark I like to talk about, especially on Heroku, this is true. If you're spending more per month for hosting a web application with Ruby, if you're paying more per month than you have requests per minute, then you are probably overpaying. You probably are using too much hardware to deploy your application, okay? So if you have an application that does 3,000 requests per minute and you're spending $6,000 a month, I think you could probably reduce your spending to the point of about $3,000 per month, okay? So that's kind of a rule of thumb to give you an idea of whether or not you're overscaled or not. Okay, so outline of this talk. First, we're going to talk about some math, some queuing theory. It's very simple. It's not intimidating. And then we're going to talk about what that math means for your Rails or Ruby application. And then we're going to use the math in the real world. I have some numbers pulled from previous talks of other engineers at big companies, and we're going to use the math I'm going to teach you to sort of check the things that they say in their talks. And then finally, I'm going to talk about some wrinkles, some practical knowledge to apply this math in the real world, like some of the things that prevent the math and the theory from holding in the real world. Okay, So this is just some example numbers I pulled out of thin air. If I told you we have a Ruby web application that takes 120 requests per minute, it has a 250 millisecond average response time, and the 95th percentile response time, so that means that 95% of requests are served faster than this time, and 5% are slower. That 95th percentile is 1 second. If I told you those three numbers, at the end of this talk, you're going to know how many Ruby processes this application needs to adequately serve its load, okay? Just with those three numbers. Really, you only need two of them, but we're going to talk about that later. Anyway, this is the secret. This is what I teach. So it's called Little's Law. It was developed by a guy at MIT in the US named John Little. John Little discovered that in almost any system, the number of items in the system is equal to the arrival rate multiplied by the time each item spends in the system. Okay, and John was studying, at the time, he was studying operations in business. But this law will hold just as well in our web applications. In the US, I use this example of a checkout counter at a supermarket. But I realized that in Japan, actually a lot of supermarkets still have the old style checkout where there's multiple, each checkout counter has its own line. But in the US, we have some supermarkets now. I don't know if you have these in Japan. I don't go to supermarkets in Japan. But we have a supermarket where there's multiple counters, but only one line. And someone at the front of the line tells you what counter to go to, okay? This is the same way it works at immigration counters in most countries, right? You have one line for the immigration counter, and then someone tells you which counter to go to. Okay, so this is called, well, it's many servers, but one queue, okay? So in our grocery store, if we have 10 customers enter the line every minute, so that's an arrival rate, okay? The arrival rate is 10 customers per minute. And it takes 1 minute to check out our customer. So you go to the checkout counter, it takes a minute to check out all your items, okay? And then you're done. And then we have 20 checkout counters. What Little's Law tells us is that if you multiply these first two numbers, 10 customers arriving per minute, multiplied by, okay, there we go. One customer to check out, multiplied by 1 minute. So 10 times 1. On average, 10 customers will be at checkout counters at any given time. Okay, that's the average number, the average amount of work in progress is 10 customers. So if we have 20 checkout counters, that means that only 50% of our checkout counters will be full at any given time. Okay? So if these two numbers are changed, if it's such that one of them is, let's say, it takes 3 minutes to check out a customer, right? Then the average amount of customers in the system, 30, is more than the checkout counters that we have. If that happens, then the line will just keep growing infinitely because the system can't deal with the amount of people entering the system, okay? All right, so then if we just translate this to a web application. Let's say this web application has 240 requests per minute and 250 millisecond response times. I specifically said requests per minute and millisecond response times because that's the way most people talk about these numbers. But we need the units to cancel, okay? We need a number in requests. So we have to convert requests per minute to requests per second, and then we have to convert milliseconds to seconds, okay? We need to multiply seconds by seconds here. So 4 requests per second, 0.25 second average response time means that we have 1 request being processed at any given time. So if you cracked open this theoretical application's servers at any given time, and you asked how many requests are being served right now, the answer is, on average, 1. Okay? So what does that mean? 1 request is being served on average at any given time. 1 request in parallel. Well, that means that if we know on average how many requests are being served at any given time, we can start making a guess at how many Ruby processes we need and then how many servers we need to serve that application, to deploy that application. And that means money, because that's really the number one cost on, for example, Heroku, when it comes to bigger applications, is how many dynos they're running. And if you get that question wrong, then you're probably spending a lot more money than you have to. And if you get that question wrong in the other direction, if you are using too few servers, then the application is going to feel slower than it has to for your customers. This equation, Little's Law, is going to give us a starting point for how many processes we need to deploy our web application. It's a starting point, and I'm going to talk a little bit more in a minute about why it's not the definitive answer, and we have to do a little bit of tuning for this in production. But I love using it as a rule of thumb to make sure that I'm on the right track and I'm not overscaled or underscaled. Okay, so the first wrinkle in this theoretical math I've been talking about here. Little's Law is true in the long run. Do we have any, does anyone have an economics degree? If you just raise your hand if you have a degree in economics. Am I the only one? Okay, we got one other person in the back that has an economics degree. So economics majors love to talk about the long run. The long run is like, in economics, is like 50 years. It's like the state of the system in infinity, okay? The great thing about the long run is that we're all dead in the long run. It's not actually relevant. It's not the real world. And so it's only true on the average, in some theoretical average where you sample your system 1,000 million times, okay? It can be not true from second to second. The reason why it's not true from second to second is the two components of Little's Law vary in the real world, right? So the arrival rate of web requests is going to change from second to second. 1 second, you get 5 requests, and then the next second, you get 300. And it's just random variation. That's going to happen. So the components of Little's Law are always changing. Even response times change randomly from second to second. So different parts of your web application have different response times. So like your admin section is probably 5 times slower than your customer-facing section, like everyone's is. So if suddenly you get way more traffic to your admin section, then it looks like your application slows down, right? The average response time will increase, but it didn't really increase. It's just people started using a slower section of the app more, right? So both the components of Little's Law can change from second to second, so we have to build in a little bit of wiggle room, I guess. That would be the expression in English, some fudge factor, a little bit of extra room. So to do that, we're going to have to understand where requests queue in Ruby applications. So there are really three layers that a request passes through to get to your application. The first one is the load balancer. So on Heroku, that's the dyno mesh. For Amazon people, it's usually ELB, the Elastic Load Balancer. Then sometimes there's an Nginx, like a reverse proxy that runs on the process. And then there's your actual Ruby application server, okay? Unicorn, Puma, whatever. Unicorn and Puma, I'm gonna use Unicorn, but really for the purpose of this examples, Unicorn and Puma work the same way here. So the request comes through the load balancer, maybe Nginx or H2O or something else in between, then it hits your Ruby web application server. Let's say you're running Unicorn with 4 child processes. What happens when all 4 of those child processes are already busy processing a request? So there's no free child processes on the server to process this request. The request queues, okay? It doesn't really queue. It sits in a socket waiting to be picked up by a new free unicorn worker, okay? So that time sitting in unicorn, in the socket, waiting for a free unicorn worker is that's what we're trying to reduce. That's what we're working on. When we're scaling up the number of Ruby processes, all we're doing is we're trying to reduce the probability that a request arrives at a server or a dyno or whatever, and there are no free unicorn workers or Puma workers ready to pick up that request, okay? We're just trying to reduce that probability. And because the time spent waiting for that free request is the only thing that we can change by increasing or decreasing the number of Ruby processes or servers available. We can't really directly reduce response times by scaling the number of servers up or processes up. Sometimes people use autoscaling, and the autoscaling is based on response times, right? Like that's the way Heroku autoscaling works by default. But it's kind of weird because, response times can change for reasons that have nothing to do with scaling. Like I said, if suddenly people start using a part of the application which is really slow, then response times will go up, and then you'll start autoscaling, but nothing changed in the application, so why are you auto-scaling? Really, auto-scaling should be based on the time spent waiting for an empty worker, right? If increasing workers reduces the chance that we're going to wait for an empty, a free unicorn process, then the only thing that we should base auto-scaling on is the time spent waiting for empty unicorn processes. This is sometimes called request queuing. If you've ever looked at a New Relic dashboard, as soon as you open up New Relic, it's right there on the top left. There's that stacked line graph of all, it says Ruby, Postgres, Redis. And at the bottom, you'll see the request queuing. It's usually 5 to 10 milliseconds. So that's saying that on average, when a request comes into your load balancer Nginx Unicorn, it spends 5 to 10 milliseconds waiting to be picked up by a free Unicorn or Puma worker, okay? So scaling up and down is only really able to manipulate that request queue time. So scaling up, adding more Ruby processes to your infrastructure will reduce request queue time, and reducing the number of processes or servers should sometimes increase request queue time. And we're going to talk about a little bit when that will increase in a minute. This means that everything I've told you so far should maybe catch on here. So it's very easy to see when an application is underscaled, because if an application is underscaled, request queue times will be very high. Okay, so over 20 milliseconds on average per request. That means you are underscaled. It means that requests are coming into your infrastructure and then they're waiting for an empty unicorn. Okay, the unicorns on the servers are all busy. Okay. So increasing the number of total unicorn workers will decrease that chance. But it means it's a lot harder. It's actually kind of hard to see overscaling, because there will always be some request queue times. You can't make it zero. Just mathematically, it's not possible. It'll approach the limit of zero, like an asymptote, but it won't ever be zero. So I have a lot of clients that are greatly, when I come in for the first time, they're actually greatly overscaled because somebody sometime in the past just increased the number of servers until they saw the request queue time go down. But then in the future, their throughput went down, their arrival rate went down of requests, their latency went down, and then no one ever changed the server number back down, right? So in production, we can actually just manipulate the number of processes. You add and remove servers, and if you keep removing servers until you see the request queue times just start to come up a little bit, and then that's actually the perfect point. That's exactly where you would want to be. If removing the next server increases request queue times a little bit, then stop right there. And likewise, if you have high request queue times, keep adding servers until you see request queue times go down. Another thing that is true here is that it also means that predictable response times are scalable response times. So response times that have a low 95th percentile relative to average response time, response times that are very easy to predict, that are constantly, usually the same response time, are easier to scale than an application that has a very high 95th percentile. The reason for that is just that the assumptions of Little's law, right, will hold more true if the application has more constant, predictable response times. The more that a response time of an application is unpredictable, the less the law will hold, and you'll need to build in more buffer room. And I'm going to show that in the real world here in a minute. I'm going to skip that story as I'm going a little bit long here. Okay, so here's what we know so far. The amount of work in progress, the number of requests in progress at any given time in your Ruby application is equal to the latency multiplied by the arrival rate. Get that thing here. Okay. Scaling reduces the amount of time spent waiting in the queue for an empty unicorn or waiting in the socket. Predictable is scalable. Predictable response times are more scalable than unpredictable ones. And I told you about how requests queue waiting for an empty unicorn or Puma process, and they wait in unicorn, or on that server, I should say. Okay, so real world numbers. I found this is a presentation online from a Twitter engineer. It was given in 2008, and he said at that time that Twitter had 600 requests per second. They had 180 application processes across their entire infrastructure serving Twitter, okay? Back then it was Mongrel, that was all they had. And on average, they had 300 milliseconds of average server response time. So if you run those numbers, I will just full screen this. Oh, no, you can't do that with calculator. Anyway. I think that's about readable. So that's 600 requests per second multiplied by 0.3 seconds average response time means that on average, Twitter was processing 180 requests in parallel. But I also told you they actually only had 180 processes deployed, okay? So they're running at like 100% of their theoretical capacity, you could say. Keep that in mind. All right, Shopify. This presentation was given in 2013. They said they had 833 requests per second, 72 millisecond average response time. They had 53 servers with a total across all 53 of 1,172 application processes. That was only in 2013, so it's probably way bigger now. And if we multiply those numbers again, 833 requests per second by 0.072 seconds average response time. That's about 60. So if you cracked open Shopify servers in 2016, they were serving 60 requests in parallel across their entire infrastructure, okay? Now 60 divided by the 1,172 available Ruby processes is just 5%, okay? So they had 20 times more capacity available than they had actual requests in progress at any given time. Okay, so that's like a 5% ratio to their capacity. Envato in 2013 said they had 115 requests per second, an average of 147 milliseconds average response time, and 45 processes. So that's 115 requests per second times 0.147 average response time. So 17 requests in parallel going on their servers at any given second, divided by the 45 they had available, is about 40% of the available capacity. What I have found is that most Ruby applications are happiest, they have reasonable request queue times when they are running at about 25%, okay? So Little's law, take the result, multiply it by 4, and you get a number of Ruby processes which generally results in good or low request queue times. So that factor of 4 that we're adding here is basically just a little rule of thumb that allows us to deal with the fact that our response times and our arrival rate of requests is not constant. It's not actually the same, and it varies from second to second. So just what I found is that factor of 4 tends to be a good sort of factor for Little's law to give you a number of Ruby processes. So if you were sleeping in the back and you weren't paying attention, this is the slide to wake up for and take a picture of and then go back to sleep. This is the slide that's going to save you the big bucks. So take your average response time of your application, multiply by 4, then multiply by the request arrival rate, so the number of requests per minute or second or whatever. That gives you a number of processes that you need across your entire infrastructure, okay? So divide it up amongst however many servers you have. We're going to talk about threads a little bit more in a minute, but they're just a bonus here. I don't want you to think about threads in this calculation. And then once you've deployed it with that number of processes, then adjust based on request queue times, okay? So that's assuming that you're measuring them, which you should be. So get New Relic or find another way to measure them or something. If request queue times are high, you should add servers, add processes. If request queue times are very, very low, like less than 10 milliseconds, try removing servers, try removing processes. As long as you can keep removing them and the request queue times are low, there's no penalty to continuing to remove them, okay? All right. So as an example, I have an application that has 100 requests per second and a 200 millisecond average response time. Going with this equation, I multiply 200 milliseconds by 4, so 0.8 seconds. Multiply that by 100 requests per second means that to start with, I will try to deploy this application with 80 processes. I don't have time to get into these rules of thumb. Like, I've written a lot about this online. I can talk about it more in the questions if you want. In general, most applications want to have 2 processes per core available on the server. So when you have a 4-core server, you should be running about 8 processes per server. I also have a whole nother thing I've written about on my email newsletter about why you should prefer 4+ core servers. If you're running 2-core servers, 1-core servers, that's a mistake. You need 4 cores. What we're trying to do, remember, is to reduce the chance that a request comes into a server and needs to wait for a free unicorn worker or Puma worker. That chance is much higher if you only have 1 or 2 cores available. We can reduce that chance more and more the more cores we have available. That's the 10-second version. So that just gives you an idea with those 80 processes. You know, if I have 4-core servers, I'll divide my processes among those servers in that way. Why the process? Why am I talking about processes and not threads? The short answer is the GVL. Little's law is talking about things that are being processed in parallel, like parallel with a capital P, not concurrent, right? And we don't have true Ruby parallelism because we cannot, in one process, run multiple threads with Ruby at the same time. I don't have really time to get into why that's true or how much I/O matters when it comes to that. Quick thing about containers in the real world. I had a client that came to me and told me that every 10 minutes they had a spike in their response times. And response times would double. And it was showing as request queue time was going up. So every 10 minutes, request queue times would go like through the roof. And we didn't know why. Normally when that happens, it means that requests are coming in all at once. So like someone else is calling your API every 10 minutes and sending you lots of traffic. That wasn't the case here. It turned out they were using Amazon EKS, Elastic Container Service, and their web processes were running on the same hardware as their background job processes. And every 10 minutes, the background job stuff was kicking stuff off every 10 minutes and completely draining the available CPU from the web processes. So another place that Little's Law sometimes doesn't hold is when you are running multiple stuff on the same server, okay? That's why I think everyone should be running web processes and background job processes on separate servers. All this stuff that I just talked about can only hold if the workloads are the same. If you're running on a server of the same work. Okay, all of what I've just said can be also generalized to background jobs, right? Instead of the arrival rate of requests, it's the arrival rate of jobs. So the amount of jobs coming in per minute multiplied by the average time to execute a job, right? And then that gives you the number of processes you need to process that queue. Same thing with autoscaling. I don't even know anyone that would do this, like autoscale their background jobs based on how long they take to execute. No, you should autoscale based on the depth of the queue for your background job. So if there's a lot of jobs in the queue, you need to scale up. If there's 0 jobs in the queue, you don't need to scale up at all because adding more stuff it would just sit there. Little's Law was designed, it was developed for business operations. So it's generalizable not just to Ruby, but to any other programming language, any other type of service. Your database, for example, the amount of, for your database, it would be the amount of times that you're calling the database per second multiplied by how long it takes for database operations to an average database operation. With JRuby, so JRuby threads are truly parallel, right? Like they actually can run at the same time. So instead of processes with JRuby, we're actually more concerned about the number of threads, right? Does that make sense? So instead of getting a process count at the end, we can actually use that number that we get at the end of Little's Law as the number of JRuby threads we need across our entire infrastructure. So that kind of gives you an idea of how we can also apply all this to other languages. Okay, in the future, guilds and autofibers, something that they talked about this morning, my prediction is that when it comes to server provisioning and horizontal scaling is that guilds are basically just going to be easier to use threads. So what they're just going to do is basically Unicorn and Puma and all that stuff, we're going to rewrite all that to take more advantage of guilds. And it just means that in the future, Ruby deployments are going to use a lot less memory when you're using multiple processes or guilds per server. And autofiber will basically just work like threads, except we don't have to write them anymore. I have maintained Puma, and Puma is like thread reactor and stuff. It's like a nightmare, and it's really hard to follow, and it's really hard to reason about. And in the future, hopefully, basically, if autofibers become a real thing, Unicorn is going to work like Puma does without all the thread code. So, like I talked about earlier, threads still won't really make your code execute more in parallel. It doesn't increase parallelism quite as much. So it's not going to have a huge impact on all the stuff that I talked about here. Okay, so here's what I just taught you. Little's Law, latency times throughput equals work in progress. How request queues work, what request queuing is, why it matters, what it means if it's high, what it means if it's low. How to provision servers based on that information, and then hopefully how to save some money by making sure that you're at the right scale. Thank you very much. My name is Nate. More of this stuff is available in my book at railspeed.com, and it's also available for free at my blog at speedshop.co. Thank you. I have 5 minutes for questions. Or was I perfectly erudite and explained everything perfectly? Yes, in the back.
Hello. How does Little's Law compare against other more telephony-oriented formulas like ones used to calculate Erlang units?
I am not familiar with those, so I can't answer that question.
Okay.
Leading question, or something that was probably cut for time. How do you account for the availability trade-off when you're trying to figure out exactly what to scale to and optimize?
Well, what do you mean the availability trade-off?
So the availability trade-off of overhead that you're not using is overhead you have if you lose a third, a quarter, half your servers all at once. Rare, but if you're adding nines to your availability.
Well, I have to say that, the real world example of this that I get a lot is on Heroku. And so the way that the Heroku pricing tiers work out is that there's like the two dyno types that are really cheap, the 1x and the 2x. It's $25 a month and $50 a month. And then there's the perf dynos, which are the big boys, and it's like $250 a month and $500 a month. So sometimes what happens is like I come into a shop when they're using like 1x, 2x dynos, like they're using 52x dynos. And I want to switch them to like 1 or 2 perf L dynos. And sometimes the math of Little's Law and everything works out where I want them to use 1 perf L dyno, okay? And you know, this is sort of maybe it's just because I tend to work with people on Heroku and not running their own stuff. But everyone freaks out at that point. They're like, oh my God, we only have 1 server. What happens if it goes down? And it's just been my experience that at least when you're running on a cloud provider at that sort of pass level, it doesn't really matter. There's if you're not doing your own DevOps and you didn't so there wasn't an opportunity for you to screw it up. Yeah, it doesn't really come into. I haven't had people have to worry about that. Usually outages come for most people nowadays. It seems at the platform level, like Heroku went down entirely, or Amazon went down entirely, in any case, the amount of extra headroom we're building in anyway, just to deal with variations in response and throughput time, sort of cover that availability as well, right? Like it's not earmarked for one thing specifically or not, so it tends to all just sort of come out in the wash at the end. Yeah. I mean, if you think about it, if you're overscaling, if you take my fudge factor of 4, for example, if you take half of everything down, then you kind of have like a fudge factor of 2, and just request queue times go up. So it's pretty obvious when that happens, and request queue times go up to some extent, but it's not gonna take stuff down. Yes, right here.
I want to ask about, you suggested we should have actual Ruby processes should have 4 times than work in progress processes, or 75% headroom should be there.
Yes, that's another way of putting it.
I want to ask is there any quantitative reasons for the number 4, or just
I get that question a lot. So there's actually a form of Little's Law where you can use the normal distribution and work all through this statistically and actually get a very valid mathematical reason for taking into account the actual distribution of arrival rates and latency. It's frankly beyond me. The factor of 4 is a combination of 1, my experience. So I've applied the factor 4 to my clients, and it seems to work out as a good starting point. And 2, with the 3 numbers that I showed you there, so Shopify was working at a factor of 20, of 5%, 95% headroom, another way to put it. Envato was working at a headroom of 60%. So I've just seen that I've done the division enough times with my own clients. On average, it seems to be about 4. Again, you should start there, and then when you deploy that into production, look at request queue times. So all this is just a starting point. You know, it's not to say that for everyone it's going to be 4. It's always going to be 75% headroom.
Yeah.
It's a good starting point for everyone. Try that. Go check your request queue times, and then adjust from there.
Okay, thank you.
Okay, I guess there's an afternoon break now, so I don't want to keep you guys. Thank you so much again for coming.